Buenos dias, Chemistry 30s. What's going on? We thought we would do this video just to kind of recap some of the major concepts in Chapter 13 in the Redox unit so far. So we're going to be going over some very specific concepts. I'm going to put a link in the description for when these specific concepts come up in the video, so you don't have to watch all 30 minutes or whatever of the video in order to be able to get at that concept. All right, let's go. First major concept is oxidation numbers. Now, there are some rules that you should know for oxidation numbers. Some of the rules are an ion is equal to the charge on the ion. All the charges, right? All the numbers must add up to the charge on the substance itself. Oxygen typically is -2. Hydrogen is typically +1. And then fluorine, if you ever see it, is typically -1. Those are kind of, in general, that's exactly what it is. So let's take a look at a couple things. We've got a mineral here. The mineral is dolomite. And it looks kind of weird. It's got calcium, magnesium, carbon, and oxygen in it. So let's take a look at this. And the first question you got to ask yourselves, literally anytime you see a chemical, you should ask yourself this question: is this thing ionic or is this thing molecular? And then you could also ask yourself, is it acidic? Is it basic? Is it neutral? Blah, 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 blah. But is it ionic or is it molecular? Is this thing ionic? I don't know. Is it? Yes, correct. It is ionic. And it's ionic because it starts with a metal or it starts with ammonium. Perfect. So let's try and look at some ions in here. Let's try and spot some ions. When I look at this thing is made up of, well, it's got a calcium ion. Okay, so it's got a calcium ion. It's made up of a magnesium ion, right? It's an ionic compound, so it's got to be made up of ions, right? Right? Okay, whatever. And then this thing over here, it's got CO3. Is that familiar to anybody? Hopefully is. That's a carbonate. So let's look up the charges of all of these things. When I look at my data booklet, I'm going to take a look and let's see. Calcium is 2+. Magnesium as an ion is 2+. Perfect. So 2+ and 2+. Okay, no problem. So that means this is +2 and this is +2 as well. So let's look at carbonate. A carbonate ion is right here. Carbonate, CO3 2-. So 2-. So that means that the whole carbonate ion has to add up to be -2. And if the oxygens are -2 as well, right? 3 times -2 equals -2 plus the carbon. We don't know what the carbon is. So that's -6. So the carbon has to cancel out 4 of the 6 to get -2. So carbon is +4, that's -2. Perfect. We just found out what all of the oxidation numbers are in this thing. And if you were to add up all these oxidation numbers, it would add up to the charge of the entire compound, which is 0, right? We've got 3 -2s, but we don't actually have 3 -2s. We got 2 times 3, which is 6. We got 6 -2s, that's -12. We've got 2 +4s, that's +8. We got another couple +2s, so that's +4. +4, +8 is -12. -12, that all adds up to be 0. So that's how I would go about doing that one. Now the next compound, glucose. Let's take a look at it. Is it ionic or is it molecular? Correct. It is not ionic because it doesn't begin with a metal or ammonium. So let's just apply our rules. -2 + 1 and there are 6 carbons. So 6 carbons plus, well, 12, and 6 times negative 2 is minus 12 equals the charge on the compound. Well, that cancels, so 6 C's is equal to 0. So the oxidation number of the carbon is 0. Perfect. Let us know if you have any questions. Otherwise, we're going to move on to the next topic. The next topic we want to talk about is half reactions. So half reactions, they show the oxidation or the reduction of a substance. So you often see like copper can turn into copper 2 ions by giving up 2 electrons. So this particular half reaction is showing the loss of 2 electrons. So what is the loss? Leo the line says Gur, so the loss of an electron is oxidation. So this is an oxidation half reaction. Now half reactions must show the gain or the loss of electrons. And this is how we're going to balance. We're going to balance a complex half reaction here. So let's balance this complex half reaction. First of all, we want to balance all non-oxygen and non-hydrogen elements first. Well, the only one that isn't oxygen or hydrogen is iodine. So 1 and 2, so I'm going to put a 2 in front of there. Perfect. Okay, number 1's done. Now let's add water to balance the oxygens. I see 3 on the right-hand side, so I need 3 waters on the left-hand side. We're always balancing these in acidic solutions, right? So if it's a solution, we have water available, and if it's acidic, we also have hydrogen ions available. The next step is to add hydrogen ions to balance the hydrogen. I see 3 times 2 is 6 hydrogens on the left, so I need 6 hydrogen ions on the right-hand side. And then the last thing we're going to do is we're going to add electrons to balance the charge. So what you have to do is you have to look at the total charge on the left side and the total charge on the right side, and you have to figure out the difference. Here, the total charge on the left side, it kind of looks like it's -1, but it's not. There's 2 -1s. So it's -2. The total charge on the right-hand side is +6. What's the difference between those? Please don't say 4. It's not 4. The difference between -2 and +6 is 8. So we need to add 8 electrons somewhere. Now I'm going to add 8 electrons, and if I add 8 electrons to the left-hand side, it's going to make it even more negative. And that's not what we want. If I add 8 electrons to that side, it's going to bring the total charge down to -2, which is what we want. We want those two sides to have the same charge. So this is our balanced half reaction. Some questions that I could ask you about this. I could ask you, is this an oxidation or a reduction half reaction? And when I see that electrons are in the product side, it's producing electrons, so it's losing electrons. That means this is an oxidation half reaction. Hopefully that makes sense. Let us know if you have any questions. We're going to move on to the next topic, which is whole reactions, whole redox reactions. Now, when I have a question about a whole redox reaction, there's a bunch of things that I could ask you, but specifically balancing whole redox reactions, there's 2 different methods that we could use. Some people like the first method, some people like the second method, and they're both totally identical. They get us to the exact same place. One's just different. That's all it is. So, a whole redox reaction shows both the oxidation and the reduction of species. But because one is losing electrons and the other one is gaining the same number of electrons, we don't actually show electrons anywhere in this reaction. In the net reaction, they cancel out on the reactant side and the product side, so we end up having, so you're going to have some reaction, blah, 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 turns into blah, 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 plus electrons. And then you're going to have another reaction plus blah, 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 gives you blah, 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 blah. And when we add them up, the electrons will cancel. That's why you're never going to see electrons in a whole redox reaction. You need to be able to identify oxidation, what substance is being oxidized, what substance is being reduced. You need to know which substance is the oxidizing agent and the reducing agent. And you also need to know the number of electrons transferred. That's another thing, but I forgot to write it down, so whatever, man. So let's try this. Let's try method number 1, which we call PAFU, or that's the per atom formula unit method. And the way we do this is we identify the oxidation number of every single entity in here. So let's go ahead and do that. Gold 3+ is an ion, so it's got a charge or an oxidation state of +3. Iodine is an element all by itself, so it's 0. The oxygen in here is -2. The gold is an element is 0. So let's figure out what the iodine in here is. So 3 minus 2s is -6. But we don't want to cancel out all -6. We want to have 1 left over. So we want to cancel out 5 of the 6 negatives. So this is going to be +5. So let's go ahead and identify what's being oxidized and what's being reduced. What's gaining electrons and what's losing electrons. So gold is going from 3+ to 0. Does it sound like it's gaining negatives or losing negatives? Well, it's becoming more negative, so it's gaining negatives. How many negatives? It's gaining 3 electrons per atom. And there's only 1 atom in this entire formula unit. The formula unit is just everything that's written here. There's only 1 atom there. So it's 3 electrons per atom times 1. So 3 electrons in the formula unit. And that's what we care about, the formula unit. Let's look at the iodine. First of all, if the gold is gaining electrons, the iodine has to be losing electrons. And let's see, it's going from 0 to +5. Well, that sure does seem like it's becoming less negative, so it's losing electrons. They're going, each iodine, each single atom is going from 0 to +5. So what that means is it's 5 electrons per atom. And because there's 2 iodine atoms in the entire formula unit, we need to multiply this number by 2. So there's 10 electrons. This whole substance, because each iodine loses 5 electrons, that means the whole entire substance loses 10 electrons. 10 electrons in the formula unit. And that's what we care about. So, what is the lowest common multiple between 3 and 10? Well, 3s can make 3, 6, 9, 12, 15, blah, 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 blah. But they can also make 30. 10s can only make 10, 20, 30. So our lowest common multiple is 30 moles of electrons. So this reaction is going to transfer 30 moles of electrons. Now, how can we get 30 moles of electrons transferred? If each gold ion gains 3 electrons, well, a certain number of them has to gain 30. What number do I have to put in front of here in order to gain 30 electrons? Well, I have to put a 10 in front. 10 times 3 is 30. What number do I have to put in front of here? I have to put a 3. So now we can start to balance. Now we can start to balance our whole reaction. I'm just going to erase a couple things here. So now we can start to balance our whole reaction. If I've got 10 golds, I need 10 golds. If I've got 3 times 2 is 6 iodines. I need 6 iodines. Now all of our non-oxygen and non-hydrogens are balanced. Let's balance the oxygens and the hydrogens. 6 times 3 is 18 oxygens. So I need 18 oxygens. 2 times 18 is 36 hydrogens. There's 36 hydrogens on the left-hand side. I don't see any on the right-hand side, so I got to add 36 hydrogen ions. Perfect. We should be balanced. Let's double check by adding up all the charges. All the charges on the left-hand side and all the charges on the right-hand side. 18 times 0 is 0, plus 10 times 3 is positive 30, plus 3 times 0 is 0. So that means that there's positive 30 on the left-hand side. 6 times negative 1 is negative 6. 10 times 0 is 0. 36 times positive 1 is plus 36. That adds up to be positive 30. Yes, this is our balanced, complete reaction. I know it was complicated, but there are steps in section 13.3 of our notes. So there are steps in 13.3, and you can take a look at them if you want to. Let's move on to the next method. We're going to do the exact same thing, okay? So if you like the first method, you don't have to look at the second method, really and truly, okay? But whatever. So let's take a look at the second way. We're going to do the exact same thing, except instead of doing oxidation numbers, instead of looking at the oxidation numbers, we're going to separate them into 2 different half reactions, and we're going to build some complex half reactions. So gold is going to be my red, and the iodines are going to be my blue. Sure, no problem. So let's do the gold. Au3+ turns into Au solid. How can I balance this half reaction? Well, 1 gold, good. There's no oxygens, there's no hydrogens, so I just have to balance this with electrons, plus 3 electrons. Boom. Now, is this an oxidation reaction or is it a reduction half reaction? Well, the thing that I'm starting with is combining with 3 electrons. That sounds like this thing is gaining electrons. So this is a reduction half reaction. So let's do our oxidation half reaction. The other one has to be oxidation. If one half reaction is reduction, the other one must be oxidation. Because if something's gaining electrons, then something else has to be losing electrons. Let's do this. I2 is turning into IO3 negative. I know it's the exact same reaction as before, but I want to prove to you that we get the same thing. Now, let's balance this half reaction. Balance all non-oxygen hydrogens first, so 2 of those. Then 3 oxygens. Okay, so we need 3 waters. And we've got 6 hydrogens. Okay, so 3 times 2 is 6 hydrogen ions. Perfect. This looks perfectly fine. Okay. The only thing we have to do is we have to balance out all the charges. I've got a total charge of 0 on the left side, and I've got a total charge of plus 4 on the right-hand side. And obviously I made a mistake. I'm going to go back here. We don't have 3 oxygens. We've got 6 oxygens, which means we got 12 hydrogen ions. So total charge of 0, and a total charge of -2, and plus 12 is plus 10. So I need to add electrons to one of these sides, and I'm going to have to add 10 electrons. So I'm going to go ahead and add plus 10 electrons to that side. I'm just going to move over a little bit. So now let's take a look at this. Does this look familiar? 3 electrons for the gold, 10 electrons for the iodine. Is that not exactly what we had earlier, right? 3 electrons for the gold and 10 electrons for the iodine. I don't know, hopefully this is starting to kind of work together pretty well. So now we got to cancel out. We've got our reduction and we've got our oxidation. So we got to cancel out the electrons. The only way we can do that is by multiplying this by 10 and multiplying this by 3, and we're going to combine them together. So we're going to get 10 gold ions, 10 Au3+ ions, and I'm going to forego states of matter only because I want to do this quicker. The electrons and the electrons will cancel out. 10 times 3 is 30, 3 times 10 is 30. So 3 times 6 is going to be 18 waters. I said I was foregoing states of matter and I just ignored myself. 3 times 1 is 3 iodines. 10 golds, so 10 gold. 3 times 2 is 6 IO3 ions. 3 times 12 is 36 hydrogen ions. Oh man, and that's ugly, but we got there, I think. I hope we got there. That's a hydrogen ion, and I'm just making it worse right now. I'm just making it worse. Okay, let's see. Is that the exact same thing we got? 10 gold ions and 10 gold atoms. Yes, that's the exact same thing we got last time. 10 gold ions and 10 gold atoms. 18 waters and 36 hydrogen ions. Yes. 18 waters and 36 hydrogen ions. And yes, 3 iodines and 6 iodates. So yeah, this is our balanced whole reaction. Let me know if you have any questions, okay? Let me know if you have any comments, but we're going to move on to the next one. The next kind of major topic in this unit was building a redox table or using spontaneous and non-spontaneous reactions to build a redox table. So it says build a table of half reactions and arrange the reducing agents from weakest to strongest. So find all the reducing agents and arrange them from weakest to strongest. Okay, no problem. As long as you understand that a redox table or a table of half reactions always has the oxidizing agent on the left, the reducing agent on the right. And if something is spontaneous, it's downhill. If something is non-spontaneous, it's uphill. And all we need are those two concepts to be able to make a table of half reactions. And it might look ugly at first, but we'll work through it together, whatever. So D plus A gives you D and A2 plus. This looks like it's a spontaneous reaction. So we're going to put the oxidizing agent on the left and the reducing agent on the right, and we're going to put it in a downhill order. So D plus, well, it looks like it's winning the battle for the electrons, right? It's gaining electrons. So D plus is gaining electrons. That means it's the oxidizing agent. That's the reducing agent. So the thing that's winning, we're going to put it on top. So D plus, and we're going to put A on the bottom. So far, I don't know. So far, I'm happy with this. This makes a downhill reaction. This is spontaneous. So I'll put D and A2 plus, their corresponding reducing agents and oxidizing agents on the other side. So that's this reaction done. Let's move on to the next one. D plus and G is no reaction. So obviously G has to be on the opposite side of D plus. Where should I put G? Should I put it above or below? Well, if this is no reaction, that means it's non-spontaneous. So D plus can't be higher than G it's got to be lower. G has to be above that. And we'll say G, I don't know, 2 plus, whatever, it doesn't matter. So hopefully this makes sense. D plus and G make an uphill reaction. That's non-spontaneous. Another way of thinking about it is G holds on to the electrons, so it'll go above D. Okay, no problem. That reaction's done. Let's move on to A2 plus and E. A2 plus and E make a spontaneous reaction. So let's take a look at A2 plus. A2 plus is right here. E, in order for it to be spontaneous, has to be below A2 plus. It's got to be a spontaneous or downhill reaction. So that means E is going to be below A. Okay. And it turns into E3 plus. Sure, whatever, no problem. So when I look at this, here's our table of half reactions. Let's just go back through here and make sure it makes sense. D plus and A. D plus and A make a downhill reaction. Good. D plus and G make an uphill reaction. Good. A2 plus and E. A2 plus and E make a downhill reaction because it's spontaneous. Good. Everything makes sense. Everything fits here. So here's our table of half reactions, and we could fill in electrons if we wanted to, but we care about the reducing agents. We want to arrange them from weakest to strongest. Where's the weakest reducing agent here? It's on top. The strongest reducing agent is on the bottom. So if we want to arrange these from weakest reducing agent to strongest reducing agent, it's going to go G with no charge, right? Maybe solid, whatever. Then D with no charge, then A with no charge, then E with no charge. Hopefully that made sense. Let us know if you have any questions or comments or whatever, but we're going to move on to the next concept. Here we're doing predicting redox reactions. So the basic idea behind this, there's 5 steps, okay? But hopefully it's a little bit intuitive. You have to do your major entities first, and then you have to identify any oxidizing agents and reducing agents, and then you have to see which one is your strongest oxidizing and your strongest reducing agent. Then you have to react them together. You have to react them together, and then you have to predict if it's spontaneous or non-spontaneous. Those are your 5 steps in predicting a redox reaction. Some reminders: strong acids will ionize into H+, so they will be present. High solubility ionic compounds will dissociate. Everything else stays together. Okay, let's do this. Let's do our major entities. We haven't even read the question yet. A lead pipe is dipped into a solution of hydrochloric acid. So you got lead pipe. Well, what's the lead in a lead pipe? Well, it's got to be Pb solid. And because it's an element, this thing is elemental, it's got to have no charge because elements are atoms. All right. So lead, and we've got hydrochloric acid. So that's a strong acid. So we've got H+. We've got chloride. We've got the conjugate base of it. And we always have water. Whenever there's an aqueous solution, we always have water. Okay, so let's write down which ones are oxidizing agents and which ones are reducing agents. Well, I've got lead, so when I look at my table, all the metallic atoms are on the right-hand side. And so I'm looking for Pb solid. Yeah, that's definitely a reducing agent. So this thing could be a reducing agent. I'm just going to do this quickly. Hydrogen ions, they can be an oxidizing agent. Chloride ions, they can be a reducing agent. Now water can be both a reducing agent and an oxidizing agent. So let's go through and let's find our strongest oxidizing agent and our strongest reducing agent. Start at the top for oxidizing agents. No. Yes, we've got acid, just acid all by itself. All the other acids up here are combined with something else, and we don't have those other things. We don't have acid and oxygen. It doesn't say that we have oxygen, so we can't do that. So we've got hydrogen ions. That's our strongest oxidizing agent. So this is our strongest oxidizing agent. And then let's look for the reducing agents down at the bottom. No. See, I see lead, but it's lead and sulfate together. No. Yes. So the Pb solid, that's our strongest reducing agent. So this is our strongest reducing agent. So let's react them together. So let's make the half reactions for lead. So lead is Pb solid turning into Pb2 plus aqueous plus 2 electrons. For some reason I always have a hard time writing aqueous. So this is the oxidation half reaction. Let's write the reduction half reaction. So that's the strongest oxidizing agent. So we got 2 hydrogen ions plus 2 electrons turning into H2 gas. Okay, perfect. So let's see, what's the lowest common multiple between 2 and 2? Well, it's just 2, so they cancel and we add them together. So we're going to get lead reacting with 2 hydrogen ions turning into lead 2 plus ions and hydrogen gas. Aqueous gas. There we go. Oh boy. So here's our half reaction, or so here's our net reaction, and we're basically done. We just got to go back and we got to see, is this spontaneous or not? H plus. Where's H plus? Goodness gracious, I'm blanking. Here we go. Oh, look at that. H plus is just slightly above lead solid. So this is going to be downhill. Always left to right, but downhill. So this will be a spontaneous reaction. This is spontaneous. Perfect. That is the predicted reaction when we dip a lead pipe into a solution of hydrochloric acid. Up next is redox titrations. So here we have our redox titration. And so use the following information to determine the concentration of bromide ions in the sample solution. So here we have a titration of 10 milliliters of acidified bromide with a 0.130 mole per liter potassium permanganate. Hopefully you kind of recognize permanganate, when it's paired up with something acidic, can be a very strong oxidizing agent. Okay, all right. Let's go through this. Let's go through. We got 4 trials, trial 1, 2, 3, 4, and we're going to see which information we're going to use. So when I subtract the final and initial volumes, I will get the volume added from here. So that's 13.1 milliliters. Perfect, no problem. 26.6 minus 14.4 is 12.2. Uh-oh. These values don't agree with each other very well. But let's move on, okay. 0 minus 4, 3 minus 12, 12.4. So we can already see these two are relatively close to each other in agreement. So we're going to get rid of this value. And then 13.0 minus 0.7 is 12.3. When you take the average of all three of these values, V average, it's just some real quick math, is going to be 12.3 milliliters. Perfect. So let's talk about what's actually going on here. You've got a burette, and you've got a solution in your Erlenmeyer flask. And so in here is your bromide ions. It's the titration of this, titration of your sample. So we get 10 milliliters of bromide ions, but we don't know what the concentration is. In our titrant, we've got our potassium permanganate, right? And so in here, what we're doing, we used an average of 12.3 milliliters, and it's got a concentration of 0.130 moles per liter. So we can use this information in order to be able to determine the concentration of our bromide ions. Before we do that, we got to get a chemical reaction. So we're going to have to predict the chemical reaction. When we go and predict the chemical reaction, we got to do the same thing we just did. Okay, major entities. We don't have a reaction, so we got to do it. So we have bromide ions. We've got water, obviously. We've got hydrogen ions. We've got potassium ions. And we've got permanganate ions. Because potassium permanganate is going to dissociate, right? Because it's high solubility. Okay, let's go ahead and see what is our strongest oxidizing agent and our strongest reducing agent. Let's start at oxidizing agents. No, no, yes. We have permanganate and we have hydrogen ions. So the permanganate and the hydrogen ions, that's our strongest oxidizing agent. Let's look for our strongest reducing agent. It's going to be a while. No, 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 no. Trust me. No, 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 no. Trust me. No, 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 no. Yes. Bromide ions are our strongest reducing agent. It's not water. Water is in there. It's barely, it's almost water, but it's not. It's bromide ions. Okay. So bromide ions are our strongest reducing agent. So let's go ahead and write out those reactions. 2Br minus turns into Br2 liquid or aqueous or whatever plus 2 electrons. So that's just this half reaction written backwards. That's all it is. And we've got the other half reaction, which is the acidified permanganate. Permanganate plus 8 hydrogen ions and 5 electrons. Gives us Mn2 plus and 4 waters. Perfect. So we've got our oxidation half reaction and our reduction half reaction. And I mean, hopefully it's pretty straightforward. We got to multiply this by 5 and multiply this by 2. So 5 times 2 is 10 electrons. 2 times 5 is 10 electrons. They will cancel. We just got to write out all the other things. 5 times 2 is 10 bromide ions. 2 times 1 is 2 permanganate ions. 2 times 8 is 16 hydrogen ions. 5 times 1 is 5 bromine molecules. 2 manganese 2 plus ions, and I'm going to run out of room. I always run out of room. Whatever. 2 times 4 is 8 water molecules. Good. But all we care about, remember, all we care about is the permanganate and the bromide. All we care about is the permanganate and the bromide. So now what we have to do is we have to do a little bit of stoichiometry. Now, the way I do stoichiometry might be different from other people, but the way I do stoichiometry is I I summarize all the information about a substance underneath that substance in the reaction. So let's go ahead and let's look for all the information about bromide. We know the only thing about bromide is we're using 10 milliliters every time, 10.00 milliliters. So we're using 10.00 milliliters every time, and we want to know the concentration. What do we know about permanganate? Let's go up. Titration of 10 milliliters of bromide with 0.130 moles per liter permanganate. And we know we use an average volume of 12.3 milliliters. So we're using 12.3 milliliters on average, and it's got a concentration of 0.130 moles in every 1 liter. So now let's do our actual honest-to-goodness stoichiometry. In my class, you always start with what you want. Start with what you want. I don't know. Hopefully you get it. So what do you want? You want the concentration, which is measured in moles per liter of bromide ions. That's what you want. You want the concentration in moles per liter of bromide ions. Okay? Well, let's either look for the moles of bromide on top, or let's look for the liters of bromide on the bottom. Now we could start with liters of bromide on the bottom. I know how many liters, 10 milliliters of bromide. But let's start on top. We know that 10 moles of bromide for every 2 moles of permanganate. This is the molar ratio. The unknown thing goes on top, the given thing goes on the bottom. Well, our unknown is bromide. So 10 moles of bromide for every 2 moles of permanganate. And yes, I get that this is a 5-to-1 ratio, but we're going to keep 10-to-2. That's fine. So in unit analysis, you cancel out the units you don't want in order to keep the units you do want. So we don't want moles of permanganate. Let's cancel that out with something that has moles of permanganate. Permanganate, something with moles of permanganate. So we're going to use the concentration. 0.130 moles of MnO4 minus over 1 liter of MnO4 minus. What this means, there are 0.130 moles of permanganate in every 1 liter of permanganate. So we've successfully canceled out moles of permanganate with moles of permanganate. Good, because we did not want that unit. Now we've got liters of permanganate. So let's cancel out liters of permanganate. I go under permanganate and I look for liters. Good. 12.3 milliliters of permanganate. I'm running out of room. I always run out of room. So we successfully cancel out liters of permanganate with liters of permanganate, and we got milli left over. So we have our units that we want. Moles of bromide on top. We just need to put liters of bromide. Well, I have liters of bromide. We ignored it at the beginning. 10 milliliters of bromide. So we've got our liters of bromide and our moles of bromide. Those are the units that we want in the end. And hopefully it's not too much of a stretch, but let's take a look at this. The milli and the milli cancel each other out. So we're only left with moles per liter of bromide. When we do this on our calculator, you're going to take 10 times 0.130 times 12.3 divided by brackets 2 times 1 times 10. You can ignore the 1 because whatever. And you're going to get a concentration of 0.7995 moles per liter of bromide ions. And if you were to write that down on your test, you would be wrong. Hopefully, you're not mad at me, but we just have to go back and we have to look at our significant digits. We've got, in our calculation, we've got 3 significant digits, 3 significant digits, 4 significant digits, and the 10 over 2 is infinite. That's a definition. That's an infinite number of significant digits. So we need to round to 3 significant digits. Here is our 3 significant digits, 799, but the 5's going to round it up. So we're going to be left with 0.800 moles per liter of bromide. That is the concentration of bromide ions. Whoo! This video was pretty long. It's 40 whatever minutes long, okay? But remember, you can always go through and I'll put in the description of this video the links to when the times are. Let us know if you have any questions. Come see us in our office hours if you want a better explanation or a longer explanation or something. Just a reminder, you don't need to go to your teacher's office hours. If you can't make your teacher's office hours, you can go to somebody else's. Thank you very much, and have a good day.